Another truly fantastic application of first-order ODEs is Newton's law of cooling. As it says here, Newton's law of cooling says that if you have an object of some certain temperature in a room or medium or whatever with this other temperature, then its rate of change is proportional to the difference in the temperatures, which kind of makes sense. If you've got something in a hot room that's super, super hot, it's going to change temperatures faster than if you put like a piece of hot something in this other thing that's hot. It's not going to change that fast because they're already practically the same. That was an amazing description. So if you don't understand thermodynamics by now, there's not much I can do for you. So anyway, looking at this definition, we can turn this into a differential equation. So the rate of change in temperature, so this is weird because you've got two different kinds of T's. So if you're doing your T's like this and like this, you have to be careful because these end up looking the same, which is why my T's have a little squiggle on them. It also helps you keep them from being a plus sign. But in any case, dt dt, temp dt, is equal to, now I'm going to say negative, and you'd be like, why is it negative? Like, because Newton says so, that's why. But we make it negative, and the reason that we make it negative is because K is going to be greater than 0. This is called our temperature constant. Temperature constant. And it's kind of cool because if T is greater than Tm, so you think about that. So if T is greater than Tm, this right here will be positive. Yes, positive. Positive times a negative is going to give you a negative. So what's going to happen is you're going to have a net negative change, which makes sense because the temp is going to decrease. So basically, if the temperature of, if I put a pot of boiling water into a cold room, the boiling water will eventually get cold. So it's got a net negative change. That's really all that is. Similarly, if the T is less than the medium, then this value right here will be negative. A negative times a negative is a positive. So if I put an ice cube outside in Texas, obviously there's going to be a net positive change. So that's just kind of how we set it up. It's Newton's law of cooling. We also kind of assume, well, I'll put this in here, we assume that the temperature of the medium is constant, which really isn't true because if I put, an ice cube outside in Texas, it's somehow like changing the environment because it's like, dissipating cold into the world, but not really. So we're just assuming it's constant. It'll be fine. So there you go. So we have this lovely little diffie Q. We're going to go ahead and solve it. We're going to move all the T's to one side, and we're going to leave the K over there. Negative K dt. Integrate both sides because it makes us happy. Natural log of T minus Tm. Negative KT plus C. Plus C plus C. Da 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 da. And we go do 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 do. And I can just move that stupid C out front. Like that. Beautiful. Okay, so T is equal to Tm equals plus C e to the negative kt. Now we're going to do something amazing. It's only amazing if you watched any of the other videos, or maybe it's amazing anyway. So if we assume that at time 0 we have an initial temperature T, then that means at T naught, Tm plus C e to the 0, which is just 1. So C is equal to T naught minus Tm. So the temperature at any given time is equal to Tm plus T naught minus Tm e to the minus kt. Now if you've watched some of the other videos, or if you know anything about this kind of stuff, you should go, oh my goodness, this is crazy. This is the transient steady state thing, and you'd be right. So check it out, right? Over a long period of time, this is the steady state. Because eventually the temperature of my whatever thingy is going to turn out to be the temperature of the medium. So as time approaches infinity, and we can look at that, as t, little t, approaches infinity, T is going to be Tm plus T naught minus Tm e to the negative k infinity, but we know that anything divided by infinity is going to 0, so at infinity we've got this steady state T equals Tm. Then right here you have your initial condition, and again your steady state. So we see the same format again, even though it's a totally different type of problem. And then this is called your transient response. It's also kind of cool because if you put t equals 0 into this equation, you're going to get the t naught out again. So this is really, really cool. You see the same thing over and over and over again, the steady state and the transient response. So you want to start getting used to this. So let's look and do a quick example. Alright, so this is the problem we're going to look at. It says a ceramic insulator is baked at 400 degrees C, then you put it in a room with 25 degrees C. After 4 minutes, it gives you the temperature, and you have to come up with what the temperature is going to be in 4 more minutes. So we'll say 8 minutes total. So a total of 8 minutes. So now it doesn't tell you the Newton's cooling thingy constant. So this is something that you're going to have to come up with on your own. It doesn't tell you the temperature constant. So our first step is to find the temperature constant. Okay, but we know that our formula is given in the form T equals the steady state plus the initial condition minus the steady state times e to the negative kt. This is actually kind of cool because for a lot of things you can just remember that this is what the solution looks like. That means you don't actually have to do all the math behind it. So the current temperature would be, say, 200 degrees. The steady state is going to be 25 because that's where it's going to end up, plus the initial condition minus the steady state is e to the negative k, and it's been 4 minutes. Now, it's a question of now, should I convert that to hours? Should I leave it in minutes? In truth, the k is going to have units on it. If you look it up in a book, the units are going to be 1 over seconds, or it'll be 1 over minute, or it'll be 1 over hour. And the reason that the units are 1 over seconds or whatever, or 1 over minutes or whatever, is because if I plug this in, I'm going to have 4 minutes. So these are all Celsius. So here's a unit discussion. So Celsius minus Celsius is still Celsius. Celsius plus Celsius is Celsius. The only way that can happen is this has to be unitless. The only way that that can be unitless is if K has units of 1 over minutes or 1 over seconds. So if you had a book, it would tell you that the time constant, or the, temperature constant is 500 1 over seconds, or 32 1 over minutes, and just whatever it happened to be. So then you'd have to use the same units. Now, since we're making it up ourselves, we can find the value of K in whatever units we want. So if we want to use minutes, we're just going to go ahead and use minutes. So, oh, and this would be degrees too, because degrees plus degrees times something unitless is still just, 2 in Celsius. So anyway, or degrees. Anyway, so I've got that 200. Well, I can subtract that off. So I've got 175 is equal to 375 e to the negative 4k. And just for fun, I'm going to do this without my calculator for a while. So I have e to the minus 4k. If I divide the top by 25, I get 715. No, that doesn't make sense. Maybe it does. How many are there? Yeah, 15. Okay. So I've got equals 7 over 15. So the natural log of 7 over 15 is equal to negative 4k. So k is equal to negative 1/4 natural log of 7 over 15. Like that. So that means I can put together my equation. So the units, I can go ahead and give you an actual value for that if you want. Natural log, where's my stupid natural log button? Natural log of 7/15 times negative 0.25, 1.190, 0.191. So since we're in minutes, if we were going to look this up or put this into a book, we would actually label it 0.191 1 over minutes. So just to be amazing, that's what we do. So that means that in general, my format is going to be that my whatever temperature I'm at is going to be equal to 25 plus 375 e to the negative negative 1/4 natural log of 7/15 times t, whatever the current time is, like that. Now I can do some math to make that a little bit prettier. So maybe I'll do that just because it's fun. I like doing math. Alright, so let's see. E to the natural log 7/15 7/15 to the, because it's times that, t over 4, like that. So 25, 375, 7/15 to the t over 4, like that. That doesn't look right. No, it does look right. I'm just being weird. Okay, so there's my equation to describe whatever's going on with this thingy that I made in a pot. All right, so the question is what is the temperature going to be in 8 minutes? So I can say in 8 minutes, I've got that the temperature is going to be 25 plus 375 times 7/15, 8 over 4, which is kind of nice because that just means squared. So if I do some more math, because this is what all the cool kids are doing these days. 15, I don't want to multiply that in my head, but I know that 375 divided by 15 is going to give me 25, because I did that a minute ago. And then I can divide by 5 again to get 3 and 5, so that's better. Okay, whatever 49 times 5 is. Why is she doing all this without a calculator? Just to prove to you how awesome I am, that's why. Alright, so I've got 245 over 3 plus 75 over 3 is 320 over 3, which is some kind of other number. See, I can't do this because this is actually like long division. 106? Yeah, and 2/3. So approximately 107 degrees. So it kind of makes, so after 4 minutes, it goes basically down by a half. So think about it. So we got to kind of think about it and make sure. So we said it started out at 400. In 4 minutes, it went down to 200. In 8 minutes, it went down to almost another half again. So this kind of makes sense. So you're kind of getting this kind of thing going here, and it's going to level out at 25 degrees. So this is pretty cool. It kind of gives you some more experience with working with these diffie cues and sees what you can get with them, and we'll take it from there.